Alright, welcome to your next to the last video for CSE 222. So today we want to talk about what are called AVL trees. And these are a type of balanced binary search tree. So we've talked about BSTs before, and we know that, in general, a binary tree looks something like this. Right, that's a binary tree, and the only requirement is that each node has 0, 1, or 2 children. Every node has a parent except the root. There's no cycles, and so on. And in a binary search tree, we have this other property that for any node, everything to the left is smaller, everything to the right is bigger. So this is a perfectly fine binary tree, and if we had numbers in here, where things on the left are smaller than things on the right, it would be a BST, binary search tree. But this is not balanced, right? So we talked about what it means for a tree to be balanced. And if you remember, it means that either the tree is empty, right? So empty trees are balanced, or the following conditions are true. The left subtree is balanced, the right subtree is balanced, and the heights of the left and right subtrees are close to each other. So this tree is clearly unbalanced, right? The right subtree is balanced. This we can probably see as not balanced, but in particular the height. This subtree has a height of 0. This has a height of 1, 2, 3, 4, 5, 6. This whole tree is unbalanced. And the reason we want trees to be balanced is because that affects the amount of work we have to do when we work with a tree to either insert, delete, or search. The amount of work we have to do relates to how deep we have to go in the tree. All of our recursive algorithms basically work by moving from the root down to left or right subtrees, usually until we find something or we get to a leaf node. And so the distance to the deepest leaf node, that's the height of the tree. That governs how much work we might have to potentially do, worst case. So what we would like is a tree that is as full as possible, so it's as shallow as possible. So here we have a tree. It has 12 nodes in it, and it's got a pretty tall structure to it. But 12 nodes we could also store like this. So there's 7. I'll put it over here for space. Right, so here's a different tree containing 12 nodes, and the distance from the root to the deepest node is 3, whereas over here the distance from the root to the deepest node is 1, 2, 3, 4, 5, 6, 7. So we can get to any node in this tree with only 3 operations, whereas in this case some of these nodes take 7 operations. So there's a great interest in keeping trees balanced, in trying to make sure that that as we build up our tree or modify it by deleting nodes, we keep this property of being as filled up in the higher levels as possible before we go to the deeper. And generally that means, we would want to fill in things here, if possible, before we start filling in things over here at a deeper level. And we can't keep a tree perfectly balanced, right? For example, if we have 2 nodes in our tree, well, it's either going to look like that or like that. And, the left side has more than the right, or the right side has more than the left. But these are still balanced trees. So let's remember our definition of a balanced tree. So T is balanced if T is null, or T left and T right are balanced, and the height of the left subtree minus the height of the right subtree has an absolute value less than or equal to 1. So that's our definition of a balanced tree. The left and right subtrees have to be balanced and close to each other in height, or the tree has to be null. Alright, so in general, if we just take an arbitrary tree like this one, and we say, how do we balance this? Well, that's hard to do. But what is not too bad to do is if we have a tree that's balanced and we add one node to it and that addition unbalances the tree, we can correct the balance. And that doesn't take too much work. So let me make a node with some values. So there's a binary search tree. Make that 300, right? So that's clearly balanced, and I might add a 10 over here. And this is still balanced, right? This tree is balanced, that tree is balanced, this tree has a height of 1, this has a height of 0, no problem. Now suppose I add a 5. So I would put a 5 over here. Well, this tree is no longer balanced, right? And the problem is the right subtree, this has a height of 0, the left subtree, this has a height of 2. 2 minus 0 differs by more than 1. But we can adjust this and turn it into the following. We can turn it into this tree. And so the right subtree is balanced, the left subtree is perfectly balanced. The height of this right subtree is 0, the height of the left subtree is 1. This is balanced. And it stores the same information as this, right? It's got the same 5 numbers in it, and it's still a binary search tree. The 10 is bigger than the 5, smaller than the 20, all of this is less than the 40. And the way we got from here to here was by doing something that we're going to call a rotation. And the way we picture it is we say we rotated around the 10. So let me show you with a visual aid here. Here's the 5, here's the 10, here's the 20. What we did is we took that line of 3 nodes and we changed it to look like that. There's the 5, there's the 10, there's the 20. We can take something that's above the 10 and move it to the right, and we'll still have that fundamental binary search tree property, that this node is bigger than the thing on the left, smaller than the thing on the right. But when we take a structure like this, 1, 2, 3 nodes, and we change it into something like this, right, we decrease the height of this, in this case, 3-node structure from having a height of 1, 2 to having a height of 1. So that's kind of the essence of how all of these rotations are going to work. And the whole trick now is knowing how we should rotate and where we should rotate and when we should rotate to take a tree that's unbalanced and turn it into a tree that's balanced. So I've posted on Canvas a cool little table. This comes from Wiki Commons, showing different ways that we can do rotations. So this is the rotation we just did. We had 3 nodes sitting like this. We took the 5 and brought it down to the right of the 4. We moved 4 up to be the root of this little tree. We left 3 as is, and the children of 3 stayed the same. The right child of 5 stayed the same, and the left child of 5 became a right child. The right child of 4 became a left child of 5. So let's work through some of these examples. And to know when to rotate, we need to do one more thing. This is something we already talked about also. We need to look at the balance factor. So remember, balance factor of a node equals, we're going to say the height of the node's left tree minus the height of the node's right tree. So this 5 down here, left and right subtrees are null. They both have height minus 1. The difference is 0. This 10, the left subtree looks like this. This has a height of 0. The right subtree looks like this. That's a height of minus 1. 0 minus minus 1 is 1. This 20, the left subtree is this. That has a height of 1. Right subtree is null. That's minus 1. 1 minus minus 1, this has a balance factor of 2. The 40, left subtree has a height of 2, right subtree has a height of 0, so this has a balance factor of 2. And the 300, left and right children are both null. This has a balance factor of 0. So we've done this in a previous lecture, previous problem set. You worked out balance factors for different trees. When we find a node with a balance factor of 2 or minus 2 or bigger, we know that the tree is unbalanced. A tree will be balanced if and only if all the balance factors are 0, 1, or minus 1. All right, so let's practice applying these rotations, identifying what case we're in, and then making the adjustments. So let me start off with our same tree. So this was our original tree. This has a balance factor of 0, 1, 1, and 0. So the tree is balanced. And then what we're going to do is add one node. So we're going to add a 5. And so, you know, the usual recursive approach, go to the left, go to the left, go to the left, put the 5 down there. All right, this has a balance factor of 0, 1, 2, 2, and 0. As soon as we find, starting from the node we inserted, we move up. As soon as we find a balance factor that's plus or minus 2, we've got an imbalance. And we need to identify what kind of imbalance we have. So if we have an imbalance of 2 and its left child is minus 1, that's this left-right case. That's not the situation. These right-right cases, the imbalance has to be negative. But this situation, the left-left case applies. The imbalanced node has a balance of 2 and its left child has a balance factor of 1 or 0. We're in the left-left case. And so the prescription is change this node 4 to be the root, bring its parent down to its right, and if this 10 had something hanging to the right, that would be adopted by 5. Well, this is a much simpler case because we don't have any subtrees A, B, C, or D. So I'm going to say this is node 3, this is node 4, this is node 5, and the balance procedure is bring node 4 up to the top, bring node 3 down to the left, bring node 5, that's our 20, down to the right. And all we're doing is rebalancing this part, so everything else in the tree is going to stay the same. And now if we find the balance factors, everything is balanced. Alright, so that was a left-left case. It's called left-left because this is the node that's imbalanced, and the tree is too heavy to the left of that, and it's also too heavy to the left of this node. But there's another possibility, which we call the left-right case, where the whole tree is too heavy to the left of 5. That's the left part. But if we look at that subtree, it's unbalanced to the right. That's the left-right case. And in the left-right case, first we do one rotation that changes it into a left-left, and then we apply this rotation to make it balanced. Alright, so here's our tree so far. Let's go ahead and add another node. So let's say add 25. So we put a 25 down here. Alright, this is balance. This is a balance of -1. This is 0. This is 0 and 1. So this is -1. This is still balanced. And the right subtree has a height of 0. The left has a height of 2. So the 40 is unbalanced now. Alright, let me just redraw this tree so that we have more space on the page. So we've got a 40, left child of 10, 5, 20, 25, and 300. It's a balance factor of 0. And there's our balance factors. All right, so first thing we have to do is identify what kind of imbalance we have, right? Here's the first node with a factor of 2 or minus 2, and its left child has a factor of minus 1. This is a left-right case. So we need to do a rotation, first of all, to change it into a left-left case. All right, so what does this rotation look like? I'm going to identify this as node 3, identify this as node 4, the 40 is node 5. All of this stuff over here is subtree D, so I'll just draw that in a triangle. The left of node 3, that's subtree A, and then the 20 has nothing on the left, and on the right it has a 25. This is the subtree called C. And now we're just going to redraw that tree using this left-left case picture. So the root is still going to be 5. That's our 40. It's still going to have D on the right, which is 300. But the left child of 5 is going to be node 4, which is 20. The right child of that is still going to be what it was, node C, so that's going to be our 25. The left child of 4 will be node 3, which is 10. And then the left child of 10 will be node 3. And then subtree A will continue to be on the left of 3, so subtree A was just our 5. Subtree B didn't exist. Subtree C we put to the right of 4, and subtree D is still to the right of 40. So we've changed it from this original left-right case into this case. And so if we look at the balance factors, again, this is 0, this will be 1, this will be 1, this will be 1, this will be 0, and over here we have a balance factor of 2. So now we've got a left-left case, balance factor of 2, balance factor of 1, and so we're going to rotate about the 20 to balance this. So the prescription here is we're going to take the node with a balance factor of 1, we're going to make that the root. So 20 is going to come up to the root. Its parent is going to go down to the right. That parent's left and right, parent's right child will stay the same, so that was the 300, that was our D, so that stays the same over there. And then the left child of this is the node with the balance factor of 1, so that's the 10. And then the left child of that node, which is, just subtree A, that's just going to stay exactly the same. And so our tree changes into this structure. And if we look at balance factors, you can see the tree is perfectly balanced. Now, we could have gone directly from here down to here by using the picture. Take node 4, which is a 20. Make that the root. Right child should be node 5, which is a 40. Left child should be node 3, which is a 10. Subtree A goes to the left of node 3, so that's our 5. Subtree B didn't exist, right? That was the node to the left of this node, which is null. Subtree C goes to the left of node 5, and subtree C is a 25, so that goes over here. And subtree D goes to the right of node 5, so to the right of 40, so that's subtree D, which is 300. And yeah, I missed the 25 over here. When we do our left case, this 25, that's subtree C that goes to the left of node 5, which is right there. So it changes into this. But this is even better balanced. All right, so everything's as perfect as it possibly could be. So we can go directly from left-right into the balanced case by just doing these manipulations, and that's probably easier and, as you saw, less error-prone for a human. But in a computer, we would typically do these pre-rotations first to change from left-right to left-left, or right-left to right-right, and then we go ahead and we have code for going from each of these to the balanced case. And if we have these cases, we do the pre-rotation first, and then do the single rotation to balance. So that's all there is to it, right? This is our balanced tree. And let's go ahead and add, let's add 30. So 30 is going to go over here. And this will have a balance factor of 0, minus 1, 0, 1, 0, 1. And this looks like minus 1, right? So all I'm doing is I'm looking at the height of the left tree. That's a height of 1. The height of the right tree is 2. 1 minus 2 is minus 1. So adding a 30, we're still balanced. But now let's go ahead and add 27. Well, that's going to come down over here. And this is going to be unbalanced. So let's do the rotations for this tree as our final example. So let me copy it over here. Here's 20, 10, 5, 40, 25, 300, 30, 27. All right, so let's calculate balance factors. So this is a 0. This is 1 minus 0 is 1. This is 0. This is negative 1 minus 1. This is negative 2. We're unbalanced. And our type of imbalance is a right-left case. Negative 2 right there, and its right child is a 1. This is right-left. All right, we're only going to have to work with this part of our tree. So we're going to balance that using these two steps, and then we're going to replace this circle part with that balanced tree. So let's just look at this. Here's a 25, a 30, and a 27. That's factor of 0, 1, and negative 2. All right, so this is node 3, this is node 5, this is node 4. So what we're going to do is we're going to leave the 25 where it is. And then we're going to basically swap 5 and 4 with each other. So this bottom node will come up here, and this middle node will go down to the bottom. And if there were subtrees, we would carry those trees around as appropriate. This node subtree would stay over here, and so on and so forth. All right, so now we have a tree that looks like this. And that's the right case, negative 2, negative 1, or 0, right? And the way we balance this is we bring the middle node to be the root, we bring the old root to be the left of the middle, and we leave the right node the same. So this will go to 27, 30, 25. And that's, again, that fairly simple to visualize rotation. 25, 27, 30, and we just change it like that. 25, 27, 30. All right, well, that's the balanced version of that subtree. So after doing our right left and our right right, we end up with the following. Sorry, the root is 27, and then the right child is 30, and there's our balanced tree. So final balance factor calculations. right? Everything is perfectly balanced. So this table is on canvas, and for the practice problems you're going to work with first calculating balance factors, and then you're going to take some trees and apply these rotations to keep them balanced. And a good way to practice this is to start with, you know, a small or an empty tree, and keep adding data to it, and each time that you add data, see if the tree is unbalanced, and if it is, make the necessary adjustment to rebalance it. It's a little tedious, and it's definitely a little confusing, but once you get the hang of it, this will all make sense. So if you want to code this, it's actually a little easier to code than it is to do on paper. Certainly less error prone once you get it locked in. But the trick to coding it is just go ahead and make pointers to all of the areas of your tree of interest. So I might call this node 5, node 4, node 3, and I could call this A, B, C, D, just as they're labeled here. And once you've got those set up, how do I go from the left case to the balanced case? Well, the root of my tree is going to be node 4, right? So that brings node 4 up to the root. Nothing changes on the left of node 4. Left node is 3, and 3's children are the same. But node 4, right, should be just equal to whatever node 5 is. And node 5's right child is D, but node 5's left child, node 5 left, becomes subtree C. And I can make all of these assignments if I know what the root is. If I call the root node 5, I can say node 4 equals node 5 left. So that's node 4, and then C equals node 4 right. And that's all I need, right? A, B, and D aren't affected by this, and node 3 never comes into play. So if I wanted to actually code this, here's a snippet of code for this left case, and you know, got some ASCII art here to show you what's going on, so I don't have to keep digging up this piece of paper. So I just copy this from this table, and here's left. There's the numbering and lettering of my nodes and subtrees. This is the case I'm in right now with the balance factors. This is the case that we are going to. And if I pass the root of a tree that needs a left adjustment, well, I initialize my nodes to be null, and this is just boilerplate stuff. And I set node 5 to be the root, right? So node 5 is the root of the tree. I set D to be node 5 right. Well, I didn't have to do that because I never used D, but I did anyway. Node 4 is node 5's left. And you got to watch edge cases here, right? Make sure before you say that you're going to do something with N4 right, make sure N4 is not null. So you have to pay attention to edges. But C is N4's right subtree, and node 3 is N4's left. I didn't need most of those. And then the actual adjustments I make, N5 left is equal to C, right? And that's what we wrote here. N5 left is C. N4 right is N5. Well, that's what we did here. And then we return N4. While this adjustment is supposed to return the root of the adjusted tree, we return N4 because N4 is the new root. So there's, you know, the left adjustment code. And the other cases are no more difficult, right? Right's going to be symmetric, and left, left, same idea, right? The root's going to stay the same. Root right is going to stay the same. Root left is going to become node 4. Node 3 left is going to become A. Node 4 right is going to stay the same. Node 4 left is going to become B. But use temporary variables, right? They make your life a lot easier with this. Don't try to do something here like, say, node 5 left equals node 4 right, right? Well, it is true. If I look at node 4's right, that's going to become node 5's left. But I'm also going to change node 4 right to be node 5. And if I do that first, and then I say node 5 left is node 4 right, well, I'm going to make node 5 left point to itself. All right. So if you try to just work from here and describe what you want to have happen, you can get tangled up by doing things in the wrong order. So make yourself temporary variables. Variables are free, right? We're not even mallocating any space for these nodes that we're creating. These are struct node pointers. We're just, having temporary variables that point to things that already exist. So this is extremely, inexpensive, and it makes your code, almost self-documenting. N5 left equals C. Oh yeah, N5 left is going to be equal to C. That's what I want to have happen. N4 right should be set equal to N5. Oh yeah, N4 right should be equal to node 5. Right? And have faith that node 5 will have the correct children, right? Because, we set the left child here and the right child was D to begin with, and we haven't changed it. So coding this stuff helps make it clearer, and it's really fantastic when you get it to work. It just feels really good. It kind of solidifies all of that understanding. All right, that's AVL trees and tree rotations. Go ahead and practice this stuff in the practice problems. I'll see you next time.